we will use two words. Maybe elements will come more often and are called, the numbers are called elements, or sometimes we will use also terms of the sequence. Okay, so now what is a series? A series is a sum of a sequence, sum of elements of sequence, not necessarily all the sequence, the sum of elements of a sequence. Okay, so for instance, we can say this is a sequence, the one we started with, 3, 6, 9, 12, and so on. And a series is, a corresponding series will be, for instance, 3 plus 6 plus 9 plus 12 plus 15. So 1, 2, 3, 4, 5. And we will just use S for sum with N. So here maybe the sum of the first elements, 5 elements, we will just refer to it as S sub 6. And of course, this can be also used to, if we call this element is A1, A2, or A0, start with 0, 1, A2, A3, A4. So this here, the same here will be equal to A sub I, and I is from 0 to 4. Okay, so in this case, you have A0 plus A1 plus up to A4. Series is a sum, and the sequence is just a list. So in general, we will talk now about the different ways of notation. So notation, now in literature, I saw different notation. Here I'm going to use for a sequence a very simple just A sub n enclosed within parentheses. So this would refer to the entire sequence, and the term an will be having a definition. So this notation colon with it will define the general term of the sequence. Okay, which as your colleague mentioned before, it's the pattern that allows you to guess what's next. And for instance, in this example, by just adding 3 to the previous element. Okay, so in some literature, some other literature, you might see something like an, and here you have n is in n or whatever. Sometimes you see an, and here you see n equals 0 to infinity or whatever. So this is just for your information that, as I mentioned always, you need to stick to the notation used by the author of the resources you are referring to, whether it's a book or online resource or whatever. Basically, I'm going to use this one, very simple, to refer to the sequence, and this one to refer to the definition, the defined term, the general term. Any questions before we move to defining a sequences in a more formal way? So questions? Okay, all right. So let me just I don't know where is it. Okay. Here. Definition. Maybe I need different pen. Okay, so we have formal definition for the sequence definition. Okay, a sequence is, this is another way to look at the sequence, and this is what we will be using, is simply a function with a special domain and assigns a real number to each, we will call it a sub n, to each number n. Now I'm going to add 0 here to the natural numbers. So small n is 0, 1, 2, and so on. Okay. This is equal to, of course, 0, 1, 2. So if you like, this is the domain of our mapping or our function here, as follows. Okay, so you can think about it. This is a function f, and this function f has a domain n union 0, which we also called, if you remember, w, the whole numbers. And here, each number n is mapped to an. So here, if you like, an is a real number that correspond to the number n, where n is just 0, 1, 2, and so on. And of course, if we will see that there are different ways to write it. If you can just write it in this way, it's called the explicit form. Okay, now the formula if n is called the explicit form or formula and it generates the sequence. So if you like to find any number of the sequence, you use this formula for generating the sequence. Okay, now explicit form is usually a function. Okay, it's just a function. For instance, what you do, what would you like, or what would you do to evaluate the, let me just finish, and then we will take an extensive example and see how to generate the previous example, the sequence in the previous example, 3, 6, and so on. Okay, so the explicit formula is just a function. There is another way to generate the formula if the element if we use previous elements, is evaluated using previous elements. We call this, we have what we call the recursive formula. So recursive formula, it generates the elements of a given sequence using the previous. A very, let's say, classical example for that is the so-called Fibonacci theorem or Fibonacci sequence. I think that some of you might have heard about it, that usually defines the first two elements, and then from there, for the next elements, you just add up the previous two successive elements. Okay, so this is what we call the recursive formula and the explicit formula. Now, some sequences refer to, some sequences can be given both as implicit and as recursive. Others can be given only as recursive, like the Fibonacci theorem or Fibonacci sequence. Now, important here, we will say A0 is the first element. Now, this is a very important agreement here, because also in literature, and maybe later we will also use it to agree on the first element is important for the formulas that we will develop further. Because if I assume that the first element is A sub 1, then that means the fifth element will be A5. However, if I assume that the first element is A sub 0, then the fifth element will be A4. Okay? So it's just an agreement, but it will affect evaluating the element. Okay? There will be shift between this one using A0 or A1 as the first element. Okay, the series, we will talk more about series in the next section or the next sections of this chapter next year. Okay. Now, questions? Let's go to our example, earlier example here. Sorry, the example that we introduced earlier, and see how we can now imagine if I ask you what is the 121st element of this sequence, somewhere here, position 121. Okay, then you will continue maybe here until this position, and then you count. So here you can think about this sequence here. This is n. Let's say this is n, and n is the natural number here, and then you have something here. So, and this is a sub n. Okay, so here we start at 0, 1, 2, 3, 4. So for instance, here this is A0, A1, A2, A3, and so on. Okay.
Excuse me, Professor.
So here, of course, this is in N union 0, and this one here in R. So this is how you look at the sequence. So bear in mind that it's this n is a non-negative integer, and the elements of the sequence are real numbers. Now here, how can we evaluate an explicit formula for this one? Explicit formula for this example, let me see in the chat. Explicit formula for evaluating AN. And let's see if we manage to even have a recursive formula. So let's start with the explicit formula. Do you have any suggestions? What can we do here? We can't see the example. Now you can see it. Okay, you can see the example, then give me a suggestion here. How would you give this general term here? Generate. We said that it generates. For instance, if I ask you what is the 97th element of this sequence? Enough light. Okay, so let me see. Now better. Is it better? Abu Zafar, is it better? All right, okay. Now let me see how would we generate these elements. So here, AN, general term, will be given as you plug in N, you will be getting the position. Yeah, you have here some elements ready there. No idea? Very simple one. So let's see. If we plug in 0, we will get 3. If we plug in 1, we will get 6. So here we have 3 times A plus 3N, where A is the first element. Okay, but this is true. This is the recursive form, right? This is the because you use the previous elements here. So we said that if you want to give it as a function, this is the explicit formula. Just a function. So in this case, you will be just getting. Okay. So if we have 0, we want to generate 3, we just add 1, right? So n plus 1, let's check. At 1, it gives me 1 plus 1, 3 times 2 is 6, 3, so on. So this will work for all. So for instance, here, if you want the element, I don't know, 121, then you just plug in here 21, 121, add 1, and then multiply it with 3. Now, your colleague, he said that A plus 3N, I assume that A here is the first element, right? First element. So this is one way to do it. But here, notice that the element here is AN equals A0, first element, plus 3 times N. Okay, so a 0 plus 3 times n. Notice here, because we use the previous element, it is a recursive formula, or we can just compare any two successive terms to get the term we are using, right? So this is one way to do it. Another way, you can define A0 equals to 3 and AN equals AN minus 1 plus 3 for N greater equal to 1. This is another way to do it. Usually when we talk about recursive formula, we have a terminating condition. So here in this case, this is a terminating condition for the value 0 or 1 that is usually used with the formulas that are recursive, because you need to generate the first couple of elements. Later we will see the Fibonacci theorem. So here AN means the current element will be generated by adding AN minus 1, means the immediate element previous to this one, and we add 3 to it. Okay? So either these three will generate the sequence. Okay? But notice that the recursive here, you need to know for this one, you need to know the previous to get the element. However, this one, you can think about it, the function as a function f of n equals 3 times n plus 1 or 3n plus 3. So it's each one has its advantages and also disadvantages. And sometimes because of the definition, it's not possible to use. Okay, it's not possible to get it into other form. So for instance, we will see that if you are to find let's say an explicit formula for evaluating the Fibonacci theorem, for instance, it's not that easy, because it's defined as originally as a recursive formula. Okay, so now do you have any questions so far? Any questions? Okay, now we will look at some basic types of sequences, and we try to evaluate the first 4 or 5 terms of each sequence. Okay, let's start with the sequence that is constant, so-called constant sequence. A constant sequence, which is, let me check it here. Okay, so maybe I will just, we'll have a look at types of sequences, basic types of sequences. Okay, and we will evaluate with first 4 terms. Okay, so let's start with the first type, where as I told you, I'm going to use, I don't know whether this is used in the English literature, but in German it's used very often, the constant sequence. So for instance, here we will define it A sub n, general term, then colon equal. In some literature, I see also equal, and down here as a subscript DEF definition. So this means that it's defined as C constant, and C is any real number, 1, 2, 3. So the sequence here looks like, so A0 is constant, A2, sorry, A1 is constant, the same constant, A2 is the same constant, A3 is the same constant, and so on. Okay? So for instance, AN equals 3. I define it as a constant 3, so A1 is 3, A2, and so on. Now here, if I ask you what is A100 here, it is the constant. Yeah, it's just like a constant sequence. Now, the second type is what we call the identity sequence. The identity sequence. And it's called the identity because it's defined to map each AN to this N, okay? AN is, and here, of course, N is a number, as we agreed, that is non-negative integer. So it's natural number added to it, the 0. Now, in some literature, they just start with A1. As I told you, it's a shift. I keep telling the students, conversion in some countries, if you go into a building, they just consider the first floor the ground floor. So if you start with the ground floor 1, that means the third floor will be 4, okay? If you start with the ground floor as 0 and then first floor is the second and so on, so you will be having a shift. It's just, don't get confused of that. It's just a way of labeling the elements, okay? So here we have the first element A0, it's just 0. A1 is 1. A2 is 2. A3 is 3. So these are the first elements. Okay. So let me maybe here just show you here. Let us predict here A100 will be also the constant, right? However, here, if I continue, A100 is going to be 100. I hope you can see it still. So that's why it's called the identity sequence. And I hope you can see everything now. Okay, a recursive formula, it means you generate the elements, the current element using previous elements. Okay. A typical example now in computing, these recursive functions are very nice to program because they just call the same function to evaluate it. It's just like the factorial. Yeah. Who's that asking? Hiram. Do you understand the concept of the factorial? Factorial, for instance. Okay, for now, the recursive formula, you just keep in mind, in short, we will be having the Fibonacci numbers. It is a classical, let's say, example for the recursive sequences, and I'm sure you will understand it by then. For now, just bear in mind that a formula is recursive if it uses previous terms, refers to previous positions of the sequence to evaluate the current position. Okay, and then when I introduce the Fibonacci sequence, if you still are not feeling very confident with that, just let me know, please. Okay. Now let us move to the next type of sequence, which is a very important sequence, and it has also very nice features. I will just try to list some of them. It's the sequence. You can think about it as the reciprocal of the identity sequence. I will just call it the sequence 1 over n. So here an is defined as 1 over n, but here one should note that n is just a natural number. It's not 0 because it's not defined there. Okay, now here the first element is a1, so it's 1 over 1, so it's 1. Second element is 1 over 2. Third element is 1 over 3. Fourth element is 1 over 4, and so on. So here maybe again let's predict the A100 here will be 1 over 1, 100. Okay. Now this sequence here on the side, this is 1, starts with 1. Next element is 1/2, it's 0.5, right? This one is, let's say, 0.3 period. This one is 0.25. This one is 0.01, right? If you compare any element here, you will find that any element is less than its previous element. Okay, this is a very, let's say, important way, or one important way to check whether the check whether a sequence, later we will talk about the concept of converging and diverging, whether a sequence is converging or diverging. And notice that 1 here is actually, it acts like an upper limit for the sequence. That means the sequence can't go above 1. And here, if it goes down, it will approach 0. So at a very large number, you see here, as we move down here, it will get smaller and smaller and smaller. That's why we call this one decreasing sequence, or strictly decreasing sequence, because obviously each term is, its successive term is less than the previous term. Okay, so this is what we call a sequence that is decreasing. Okay, so this sequence, as I told you, is an important one. Another sequence that is also interesting is the sequence that is called alternating sequence. The alternating means it's changing between positive and negative. So in general, let's take this one defined as -1 to the power n times 1 over n. So it's just the alternating of the previous sequence. Okay. Now this term, of course, here n is n natural number. Okay, this term -1 to the power n, it will cause the following. If n is odd, then you have -1 to the power odd. so it will be -1. So this, if you like, will generate the sign of the term. If it's an odd position, it will be negative. If it's an even position, so to the power 2, 4, whatever, then you will be getting negative squared, which will be positive. And this is how alternating sequences usually generated. Use the fact that -1 to the power odd is -1, -1 to the power even is +1. So let's see here A1. Now 1 is odd, so here I will be having -1 to the power 1 multiplied by 1/1. So here I got -1. Okay. Now at the second position, I have -1 squared times 1/2, and this is just +1/2. A3, now we are back into the odd, and this is going to generate -1/3. Now A4 is equal -1 squared times 1/4, and this is equal to 1/4. Now, here, interesting, A100, so 100 is positive because it's even, and this is going to give me 100. Now, if you ask yourself, is this, in general, do we have AN is less than AN minus 1? So for instance, here you have -1, then you have 1/2, then -1/3. So obviously here it stops here. So -1, it's not less than 1/2. So it's not in general, it's not generally decreasing like the previous one. This is because you are getting negative and positive, okay? So it's not generally decreasing because here you have -1 and then 1/2. This is greater than that one, so it's not increasing for all terms. Okay, so alternating sequences are sequences that have a strange pattern. It's just zigzagging between negative, positive, negative, positive, negative, positive. So it's hard to compare the terms because it keeps switching between negative and positive. Another sequence that is important, and in fact, these two sequences are fundamental in the also how you call it, financing, right? So investment of of bank account or interest rates and so on. This is the so-called the arithmetic sequence. So now number 5, right? 5. I hope you can see it. Arithmetic sequence. Okay, for an arithmetic sequence, usually we start by given, usually you will be given the following. First element, let's call it A0, and a number DNR, which is the constant that is the difference between two successive terms. So in general, AN is generated using the first element is 0 plus n times d. Now here, please be careful for the following. Maybe some of you saw this formula before for arithmetic sequence, but you see it rather with a first element plus n minus 1 times d. This is because you consider the a0 here rather a1. So if you have a shift, then you need to subtract 1 from n here, okay? So if you start with a0, then no need for that. So let's generate the first four elements here. So a0 is obviously a0. a1 is equal to what? a0 plus 1 times d, okay? a2 equals a0 plus 2d, but this is just equal to a0 plus d, right? But this one here is just a1. This one here is a1. So it's a1 plus a3 equals a0 plus 3d. So this is our fourth element. So it's a0 plus d, sorry, plus 2d, d, which is a2 plus d. So always the arithmetic sequence, the previous element you add to it this constant. So that's why this constant here, if you like, is the result of subtracting the next term from the previous term. Okay? And that's why, so for instance here, if we want to evaluate the 100th element, a100 is equal to a0 plus 3, sorry, 100 d, 100 times d. Okay? Now, notice here the following. For such sequences, an is equal to an minus 1 plus d. And this is the recursive formula. This is the recursive formula for this. So recursive formula means you use the previous previous element to generate the current element, okay? You just take the previous element, you add to it the constant. An example for that, we just had it in the previous example, which is 3, 6, 9, 9, 12, etc. So you can think about it. The first element is 3, then you add to it 3 times n to generate the numbers. Okay, so any questions regarding the arithmetic sequences? Okay, another sequence that is also very common is the so-called the geometric sequence. Now the geometric sequence, here you can say that difference between any successive terms, here you can write this an minus 1 is equal to d. The difference between two successive terms is constant. Here the geometric sequence is the quotient. Dividing the next term by the previous term, it's always a constant. So geometric sequence. Again, here we are given two numbers. So given usually a0, first element, and you are given the and Q, which is the number in R. Okay, now let's generate the first element. Of course, A0 is the first element. A1 equals A sub 0 times Q to the power 1. So general Q to the power N. A2 is equal to A2 equal to A0 times Q to the power 2. And notice that this is equal to A0 times Q, but this one again here is just A1. So it is here just A1 times Q. So other than the arithmetic sequence here, we are multiplying this quotient or this constant with the previous element. If you remember in the arithmetic sequence, we were adding, and this is A3 here, the fourth element, A0 times Q to the power 3, which is A2 times Q. Okay, so here, as I told you, this is the recursive formula for this one. Recursive formula here. In general, we have an equals A0 times Q to the power n. For instance, here the element 100 here, if you just continue here, A100 will be A0 times Q to the power 1. Okay, so this formula is the so-called explicit formula. This is an explicit formula. Now, as I mentioned before, the recursive formula is just dividing two successive terms. Huh? So recursive formula for this recursive formula, Q is equal to an plus 1 over an. That means Q is the constant that each two successive elements, if you divide the next by the previous, you get the same. So for instance, we will have examples later. The you all studied the so-called binary system, for instance, 2, 4, 8, and so on. If you divide any successive terms, you will be getting 2 as a constant. Okay. Okay. So now, for the guy who was asking about the recursive formula, so I hope it will be clear. By the way, in English literature, they use also R together with this formula. It's just a notation because Q and R, Q stands for quotient and R for ratio. So sometimes if you are just using any English resources, that you might have it as R instead of Q, but it doesn't make any difference. Okay, now we get to this famous sequence. The Fibonacci sequence. Now, this is, as I mentioned, a sequence. I don't know, we talked about it. You remember once we were talking about the golden ratio, which is, I don't remember the exact value, I think 1.618, 1.618 roughly, which is an irrational number. Now, this number here, it's called the golden ratio, and it's really an amazing number. You can Google it. You will be really surprised how many patterns in nature follow this, whether in plants, in animals, in just in nature, in different stones, whatever. You find the so-called golden ratio. Uh, an example for that is the spiral, and so on. But you find it in many, let's say, natural phenomena, like if you have roses, or I don't know, pineapples, or trees, or whatever. Yeah, even in music, you might find it in the Mona Lisa, in paintings, in logos of major companies, Apple, and so on. It's used everywhere in nature, in human body, compared to, the distance between the arms, tips of the fingers, and the body mass, and so on. It's really an amazing number, and it's even there is something that's called the golden angle, which is 137.5, I think. If you subtract this from 360, you get 222.5. If you divide these by, divide 2.5 by 137.5, you will be getting also this golden ratio. That's why this is called the golden angle. So it's really an amazing number. And I don't know whether I told you before how this originated. The Fibonacci. Fibonacci was, as the name indicates, an Italian mathematician. I think he had a different name, but that name, there was another famous person who has the same name. So then later they just distinguished him, giving him this name, referred to the town he came from. And he had the task to predict the out of a pair of rabbits, that are just isolated, not going out, assuming that no rabbits will die. And after giving birth, I don't know what's the cycle for rabbits, few days, maybe month. And then these rabbits will grow. After 1 year, how many will be out of a couple of rabbits for the start? So that was the task for Fibonacci, and he started with, of course, defining this sequence as follows. So A0 equals 0, okay? Then A1 equals 1. And starting from A2, AN equals just the sum of the two previous terms, for n greater equal to 2. That's all. This is all about Fibonacci's sequence. Now, the guy who asked, this is a typical example of recursive. It means the current term is just adding the previous term and the previous of the previous term. So if you just like, it's just adding the two previous terms. Okay. And always recursive, it has something like an end point. We call it a termination criteria. So in this case, criteria for termination is just getting 1 or 0. You can't go behind that. Of course, it needs to stop somewhere. Okay. So I don't know. Let me check the guy who asked. Is it clear what? So it's just here. This is a pure recursive formula. What's the name of this guy? Hiram, I think. Hiram, did you get it? What's the meaning of recursive? This element is defined. Okay, great. Now, of course, there is another definition for that, how to generate it, but it's a little bit complicated. It involves the golden ratio, of course. Now, let's generate these numbers. Okay, maybe more than 4. A0 is 0, A1 is 1. Now here, look how we use the recursive. It says here, starting at 2, AN equals AN minus 1. So in this case, it will be AN minus 1, A1 plus A0, right? And this is equal to 0 plus 1, and this is, okay? Now, A3 is going to be A2 plus A1, okay? The two previous terms. And this is equal to 1 plus 1, and this is equal to 2, okay? Okay, so 1 plus 0 will give me 1. 1 plus 1 will give me 2. Now the next element will be A4 equals A3 plus A2, and this is equal 2 plus 1, and this is, or 1 plus 2, and this is 3. A5 equals to 5. A6 equals to 8, and so on. So all in all here, you will be generating this using adding the two previous terms to each other. All right, so this is, so let's take some examples here, but if you take here the golden ratio here, ratio in this context here is just AN plus 1 over AN. Of course, here at the beginning, it's 1 almost, then it becomes maybe a little bit. So if you take 8 divided by, I don't know, 5, you get 1.6. Now, if you get larger numbers, it will be at some time, it will be almost a constant. And this is what's referred to as the golden ratio, and it's roughly 1.618. And you can Google it. This golden ratio is, as I mentioned, it has applications all over in our life, in nature, and so on. Okay, so now we will just make an introduction to our next topic. So I don't want to go deep in this. You have a mock exam, and then you will be having only a couple of topics left. So let's do the following. I will give you a couple of examples now for the in particular geometric and arithmetic sequences, but I'm not going to go into the deep into convergence and divergence of sequences. because this is related to many theorems, many techniques that we are going to introduce, and this we will do definitely after we come back from the holidays. But for now, I just want to give you a couple of examples, and after the break, we will talk about the, let's say, informal concept of convergence and divergence of the sequences. So let's have just examples. Now, as I told you, okay, given the sequence, can you see it? Is this sequence geometric or arithmetic? How can you tell? Or neither? If I ask you evaluate A100 here. Okay, I give you this sequence here, and then I want you to evaluate the 100th element. What would you do? So first of all, is it a geometric or arithmetic sequence here? And why? You didn't get it? What's the arithmetic sequence? Arithmetic sequence, you have a fixed difference between two successive terms. Arithmetic sequence, you just subtract one from the previous and see whether you have a constant. So obviously it's arithmetic, right? So here you have 3, 3, 3, right? So it's arithmetic. If you divide the next term by the previous and you got a constant, it is a geometric, okay? So it's obviously an arithmetic, and for arithmetic sequence, so A0 equals 2, this is the first element. So we said we need for arithmetic sequence the first element as well as D, and D is the difference between two successive terms, and it's 3, okay? So general term here for arithmetic sequence is an equals a0, which is 2, you just write it, plus n times d, and in this case it's 2 plus 3, okay? So an equals 3 plus, so 2 plus 3n. That means here at A100, just plug in for n equals 2 plus 3 times 100, and it's going to be 300 and I hope. Okay. So to analyze the sequence, whether it's arithmetic or geometric, just subtract previous terms. Of course, you need to compare all, okay? Here, 5 minus 2 gives me 3. 8 minus 5 is 3. 11 minus 8 is 3, and so on. Now, geometric sequences, so this is the first. Geometric sequences, you have two, let's say 4 8, 16, you know the sequence from the digital binary system. Okay. Now here, if you divide 4 by 2, 4 by 2 equals 2, right? 8 by 4, so divide by the previous 2 and so on. So here Q equals to 2, and this is geometric. And this is the first element, okay? So AN equals A0 Q to the power N. Now here, please be careful. If you start with A1, then it's Q to the power N minus 1. Okay, and this is equal to 2 times 2 to the power N. Again here, if I ask you A100 here, then it will be A100 equals to 2 times 100 to the power N. Right? 100 to the power, no, 2 to the power 100. 2 to the power 100 here. Yeah. And this is equal to, I don't know what is 2 to the power 100. You can evaluate it. 2. It's a large number. 1.2, 1.3. It's a very large number. So you just evaluate it, multiply it with 2. But this is how it works. Okay, you have to be careful. Sometimes if you have fractions, for instance, you can have the reciprocal of that. Okay, 1 over 2, 1 over 4, 1 over 8, 1 over 16, and so on. Then, of course, the quotient is Q is different here. Okay, so let's take a break now and then get back 20 minutes or 15 minutes to continue. I'll just want to show you one more thing. That is evaluating the limits, and in particular limits approaching infinity. And we are done for today. I know you have mock exam next week, and I don't want to bother you with more material because I need to repeat it then when we come back from the holidays. So let's stop now and then continue for half an hour after the break. And if you have any questions related to the mock exam, to the material before, to the worksheets before, how did you get Q? Yes, Q is actually, Q is defined, Q is the constant that has two successive terms, okay? For instance, if I have 10, 100, 1000, and so on, okay? Q is this divided by that, okay? 100 over 10. Q is this divided by that, 1000 divided by 100, okay? So dividing two successive terms, this is the ratio Q. Got it? Okay, I will repeat it after the break. Okay. Let's take the break now.